Good morning, everyone, and welcome. I see we've got a very full session today. I see already we've got 21 attendees, and obviously that's in no small measure due to our speaker, who is Gavin McArdle. Gavin is certainly very well known here in UCD for his work in smart cities and in all aspects of that. And we're delighted as well that Gavin is one of the collaborators here with the CeADAR Centre. Gavin recently won the European Union funding call with us to the tune of $250,000 to bring in a very senior academic from overseas to work on aspects of smart cities, and we're delighted to be working with Gavin on that. Now, as you know, this is a series of seminars that we've started again after the holidays in August. We have been running them twice a week up until August, and after coming back now in September, we decided to set back to one a week. And I was delighted that Juan had suggested that our own technical in-depth talks that we give actually in CeADAR would be a good mechanism to actually make available to the wider membership community. And these events are available only to our CeADAR members. And they're going in more depth than the previous presentations that we had just before August. So again, thank you to both Juan for organizing them and Lauren as well for helping out. And again, especially to Gavin. So I'm going to pass over now to Juan to introduce the talk. And I would welcome you back again let me just check this, on the 17th, in 7 days' time, because we have another speaker from CeADAR, Hamid, who's talking about the analysis of Airbnb data, and I know that he's been working with Gavin on that. So anyway, thank you all again very much for turning up, and I'll pass you over to Juan now to introduce our speaker.
Thank you, Edward. Okay. Okay. Yeah, so I just welcome to the CeADAR Tech Talk series. So I just introduce a bit the format of the talk. For each talk, we have the speaker to do a presentation from 40 to 45 minutes, and we will have a recording, according to the speaker agreement. And then after the presentation, we will turn off the recording, and you can ask questions after that. So for the presentation today, we will have Gavin, McArdle, and Gavin, the assistant professor from UCD. And Gavin will talk about cities traffic simulation, the Dublin scenario. I hand it over to you, Gavin.
Okay, good morning, everybody, and thanks very much to Edward and Juan for the lovely introduction and for the invitation to speak at this session. So the research which I'm going to talk about today is all about city-scale traffic simulation. So essentially what we want to do is be able to simulate the current state of traffic in the city so that we know where the cars are, where the traffic is, where all the vehicles are, and what's happening in terms of travel time across the city. So there's a nice slick image there of of an Asian city there. But of course for us in Dublin, what we're more used to is this kind of setup where it's rainy and we're stuck in traffic. This is the M50 motorway, and we're wondering what's going on. Why is there traffic? Why can't we get this situation sorted? So hopefully by being able to simulate the traffic, we can start to think of interventions in terms of the traffic infrastructure to help with alleviate these kind of congestion problems. So today I'm going to talk about building this Dublin traffic scenario. So it's based on a multi-agent system, and in a multi-agent system, each vehicle in this case is represented by an agent, and the agent has different goals. Obviously the goal is to get from A to B, and that's what we're trying to simulate, is the movement of vehicles from one location to another location. We're trying to create a realistic simulation of that. A big part of developing the traffic scenario is the input data. So as you can imagine, we need to know where people are and where they want to go to be able to do the simulation. And this is all called the travel demand. So the demand that's going to be on our road network, in this case, the road network of Dublin, where people live, where they work, where they want to go to school, where they want to go and shop, where they want to go and socialize. We need to know all of these things and feed it into our simulation. So we need information about the population, who owns cars, what their daily commuting pattern is like, where they want to go for discretionary trips such as shopping, where they're going to go, where their friends are, so where they're going to go to visit their friends. We also need to know the road network. So a lot of this project was about preparing the data and finding suitable data sources to build this simulation so that we could have it as realistic as possible. I'd also talk about the results and the evaluation that we carried out to assess how good we did, how good our simulation is in terms of mimicking the real traffic situation. So the motivation for having a simulation of a city's traffic is for planning. So for example, if you're going to build a new housing estate or new housing development, you need to know how that's going to impact the traffic. So you can have the current situation, add in the building project, estimate where people are going to work and how they're going to interact with the traffic and if that's going to cause additional congestion or not. Similarly, if we're going to build new infrastructure, so new roads or indeed new public transport projects, how is that going to change the current situation? We can simulate that. So in the simulation that we built, we can add and remove roads easily and see what impact that has on the overall traffic situation in Dublin in our case. Other things, for example, you may want to introduce road pricing and see what impact that's going to have on the traffic. So the agents that we use in the system can be told of the road pricing and they can weigh up the pros and cons of going on the cheaper route versus the more expensive, quicker route. We can see that impact on the traffic through the simulation without having to run expensive pilot studies or surveys of people even about their behavior. In the short term, we can have an emergency response situation. So if a road suddenly has to be closed, and if our simulation is quick enough, then we can actually see what's going to happen to the traffic situation in Dublin. Similarly, if we want to introduce dynamic road pricing, so where the price of traveling on different roads varies throughout the course of the day, we can simulate that. Likewise, dynamic speed limits. If we want to change the speed limit on a road at certain times of the day, we can simulate it. But in order to do that, we have to have an accurate base case, an accurate representation of what the current traffic situation is now before we can make these changes to see what would happen in the future. So we need an accurate simulation first, and then we can start adding building projects, adding new infrastructure, closing roads, testing emergency response, and introducing these dynamic features of travel. So that's kind of the motivation why we want to have a simulation. So the goal then is to simulate the traffic in Dublin. As I said, it's an agent-based micro simulation. So each agent represents a person, or in our case, a vehicle. And what the vehicles need to do is perform a sequence of activities. Typical sequences go from home to work and from work to home. That's by far the most common sequence of vehicle movements. But there are more complicated ones where maybe people are going to perform shopping trips, they're going to dentists, they're going to doctors. So we want to be able to have all that in our simulation as well. So we have an agent representing each vehicle. So this could be a large scale simulation, potentially millions of vehicles and millions of agents in our simulation. In our case, we worked with a population of 500,000 agents, which was roughly 50% of the Dublin population, and we scaled up our results accordingly. But potentially we could have millions of vehicles all interacting with each other. Importantly, the simulation has to handle the interactions between the vehicles themselves. So obviously when we commute from home to work, we don't have the road to ourselves. There are other vehicles, other things on the road that we need to interact with. And the simulation has to handle that. So it has to handle congestion, the fact that roads space is limited, and that there are things like traffic lights and everything like that that we need to interact with during our commute. So the simulation has to handle all that. And finally, then we're simulating just a single day. So a single 24-hour period. A typical work day is actually what we're trying to simulate to see what's happening with the traffic in that day. So we use a tool called MATSIM, which is multi-agent traffic simulation. And that handles all the routing for us. So if we tell MATSIM where people want to go or where vehicles need to travel, it will do the routing for us once we provide the the road network to it. It's a queue-based system, and basically that means that the links, which are the roads, all have a certain capacity. And if a road becomes full, the vehicles trying to access that road just start to queue. And that's what causes congestion. And that's what causes the congestion in real life. If a road is busy in front of us, we're driving, we have to just wait. We have to wait our turn to get onto that stretch of the road. And that's what causes congestion. So it's very kind of reflective of real life, this QSIM simulation. Within the simulation, the agents have strategies where they can change their plans. So you'll see how we use the data to build the base plan. That's basically the ideal situation where people want to go at the time they want to leave and the route they want to take. However, the simulation runs multiple times. It runs a couple of hundred times in order to kind of find the best situation for the simulation. And on each iteration, the agents can change the route they take. If you think about it, that's something that we might do ourselves. So we have the ideal route, the shortest path from our home to work, for example, but we find out that everybody's using that path. So the next day we might try something different. We might divert off that path a bit. Maybe it's a longer route, but we think maybe it's going to be quicker. So within the simulation, the agents have that ability as well. We can also change our departure time. So if I find in real life, I might think even 5 minutes earlier in the morning might be beneficial. The agents can also start to play around with the departure time to try to find a better travel time for them overall. Finally, then, location choice can be changed. Now, obviously, where we work can't be changed or where we live can't be changed, but other discretionary trips such as shopping can be changed. So if the agent is told they need to perform a shopping activity, there's a choice there between which shopping locations they go to, and that can have an impact on their travel time. So the agents have this memory built into them where after each iteration, they produce a score, which is the travel time, the total travel time for all of their daily activities. And what they're trying to do on each iteration is minimize that. And the tools that they have at their disposal to do that are changing the route, changing the departure time, and changing the location where they perform discretionary trips. So trying to minimize that all the time. And of course, all agents are competing for resources. And the resource that they're competing for is the road, because the road network is limited capacity. So you're trying to get your slot to use a particular road network at a given time. So they say the simulation runs multiple times before we get what's called an equilibrium, where the average score of agents stabilizes and changes to the route selection, the departure time, or indeed the location choice aren't having a very big impact on the overall average travel time for agents. At that stage, the simulation is finished and we can assess the results to see how accurate or reflective of the real world situation they are. So the MathSim workflow that we followed was firstly creating the initial demand, and that's the most challenging step actually. It's getting the data together to be able to tell the simulation where we want our vehicles or our agents to go during the course of 24 hours. Once we have that, we feed it into the mobility simulation that handles all the routing, handles all the interaction of the vehicles with each other, and produces scores. So at the end of their 24-hour simulation, each agent has details of how long their travel time was for that day. At that stage, then the strategy and the replanning can occur for each agent individually, and on their own, they can change the route, the route, the departure time, and as I said, the location of the discretionary trips. And these steps are all iterative, and this is where the simulation is running hundreds of times to try and reach this equilibrium state, and then we can analyze the results. So as I said, the initial demand is the first step and is the most challenging one, because to create an accurate simulation, you need to have good quality input data and accurate input data. And really the focus of this talk is kind of how we went about getting this initial demand and building it in a very realistic way. Okay. So the initial demand, as I said, is what people want to do. So where people live, where they work, where they go to school, where they shop, where they eat, where they entertain, where they socialize. Essentially, we need to know where people go. And this is the basis for our simulation. We need to simulate where people are going. And this is all spatial data. So it's all data with coordinates. It's all locations within Dublin City in our example. And often there are temporal properties as well, because you want to go to the shop at a certain time. The question then is, how do we get this data? So we want accurate data, so their simulation is going to be accurate. But how do we know where people do all of these different activities? So one thing we can look at is the census. So you might remember filling out the census. So in Ireland, it's every 5 years. And actually in that census, you give your address and you give the address of where you work or where you go to school or college. So that's a good basis. That's a good starting point for us, because most of the trips, it turns out, are commuting trips. As everybody knows, that's when the most of the traffic is on the road. So it's going from home to school or to work. And they're the biggest amount of trips. And we have details about that in the census. Of course, the census don't release people's individual addresses and individual work locations. So it's not possible to say where I live and exactly where I work. But they create an anonymized record of it by aggregating data to a certain level. And they aggregate it to what's called a small area unit. And a small area is actually 80 to 100 households. So it's actually quite a small area. So what we can tell is that somebody who lives in this small area works in another small area. And that's really all we know at that stage. Or they go to school in another area as well. So it's work or school is what we have details of. Small areas. This is kind of just the map of Ireland. You can see the small areas. In Dublin, it's very, there's an awful lot of small areas because it's based on the number of households. So 80 to 100, you could imagine that a single apartment block or a single housing development is all a small area. So we know there's somebody going from that apartment block to another small area in the city. And a lot of simulations stop at that place. That's all they're interested in, is going from one area to another area, and they route the traffic based on the closest road out of one area and into another area. We wanted to go a bit further to create a more realistic simulation. And I'll talk about how we did that in a minute. So in the census, we were interested in the population that that is working, essentially, to get the main commuting traffic, to understand what that is like. So we looked for people whose place of work, school or college, address was matchable, firstly, to an actual address point. So we had roughly 2 million of those, including students and workers. This is for the whole of Ireland. And then we were also able to see people who lived in Ireland but worked in Northern Ireland, or lived in the Republic of Ireland but worked in Northern Ireland. There's maybe 10,000 of those. So it wasn't a huge number, but we included them as well. Missing from these numbers are retired people who don't have a place of work and unemployed people who don't have a place of work or school. So that's where we're getting this 2 million for the population of Ireland. So just to give you an idea, I won't go in detail into this, but people may be interested in this data source. It's called POWSCAR. It's place of work, school, college, anonymized records, and it's a very big file. So it's but really easy to use. It's a simple delimited, tab delimited file. So the first row just contains all the variable names, and each subsequent row then is all the individual records for a person. I'll show you what they are in a minute. There's obviously some additional files which just tell you how to use it and what the different variable names actually mean. But there are 42 in total. It's a mix of spatial data. You can imagine why we might be interested in that for our simulation. Some data about the house itself, the building properties, about the households. It's the people who live in the house or in the building. And the individual data about the people who live there. And then some of the variables are relevant to students and some aren't. We'll just have a quick look at those, but I want to show you the ones mainly that we used for this simulation. And this is only the initial demand. So this is the demand of where people live and where they work that we're trying to figure out in this step of our process. So the residence is given at all kinds of different spatial granularity, right down to the area type, the town name. But what we're interested in is the small area. That's the smallest unit, so 80 to 100 households. So we know from the place of work, school, college, anonymized records, somebody lives in this small area. Then the place of work, again, it goes right down, different location, granularities, the town name, the small area, but it actually goes one step further for workplaces, and it creates a grid over the entire country of 250 meters squares. So we've got a finer granularity of where people work, which again is useful for us because we're trying to create a really fine-grained simulation of traffic movement. So the small area of where people live, and then we have this grid 250-meter grid of where people live, or sorry, where people work or where they go to college. So remember what we're trying to do, create this simulation of where people live and where they work. So we're starting to get some data for this initial demand. Some of the other variables that we didn't use, and again, this is just for people who might be interested in that data set. The data set is available from the CSO, obviously. It's available only to you to apply with details of exactly how you're going to use it for your research. It's not an open data source. You need to apply, and there's certain conditions to how you can use it. But the variables in there are about the household, so the number of residents, the number of workers, the number of students, and so on. Some information about the house itself, the year it was built, is it owned or is it rented, is it a one-off house, the number of cars, and some education details as well. And then information about the individuals, their age, their sex, their religion, the ability to speak English, marital status, all kinds of information, all at an individual level. But obviously it's anonymized to the small area. So you can figure out how many people of a certain age are within a small area using this POWSCAR data and using the general census data as well, I should say. So really these two slides aren't of much interest to the simulation that we're trying to develop here. Obviously the location of the houses and the work is, but this information is not really relevant. But there is another set of data as part of that data set, which is extremely relevant. And it's to do with the travel. So it's the means of travel. So do you walk? Do you cycle? Do you go in a car? Do you go in a van? Do you use public transport to get to work, school, or college? The time you leave at and the journey time. So how long it takes you in minutes to get from your home to your place of work. And if you remember, you actually filled all this information in the census. So when you were completing the census, you gave all of this information, and now it's been aggregated and shared in these files for use. So you can see how this is going to be particularly relevant to our simulation, what we're trying to do. Means of travel, time of departure is really important. Means of travel for our study, we're not interested in people who use public transport, who cycle, or who walk. So we're only interested in people who use cars or vans to for their commute in this particular study. So we were able to immediately reduce the number of individuals or the amount of data we were looking at. Okay. So to process it, we just use a spatially enabled database, and the one we use was PostGIS. So it's just an SQL database, but it has special properties to enable us to do spatial queries very quickly and efficiently. We were interested in individuals who live or work or study in Dublin. So we're trying to create a Dublin simulation. And if you think about it, people who live or work or study in Dublin is going to capture all of the traffic in Dublin. So you may live in Cork and work in Dublin. You're commuting in, you are captured by this particular query that we did. You may live in Dublin, but work somewhere else. You may work in Gavin, for example, and you're commuting out every day. Again, we capture you here because you live in Dublin. And it's important that we do capture that data because you're using the road network as part of your commute that we want to understand. So it's not just people who live and work in Dublin, it's people who live or work or study in Dublin. We also limited it to individuals who have a fixed place of work. So one of the variables in the data set we were using was if you were somebody who's on the road all the time, so you don't have a fixed office location or a fixed factory location where you work. You might be a traveling salesperson. We didn't actually capture you for the initial demand in terms of where you live and where you work. We limited, as I said, the means of travel to cars and vans. We looked at the departure time because that's really important for us to build an accurate simulation, to have the timings of it correctly. We looked at the residential small area for where you live, and we used the fuzzy east and fuzzy north grid for where you work. So that's a 250-meter grid, and we just know that somebody works in that area. We removed some anomalies. So for example, if the travel time was very far removed from actually the distance between your place of work and where you live, we removed it as an anomaly. And our numbers are so big, we're dealing with millions of vehicles, that removing some of the anomalies was not really a problem. In other cases, there was no school or college actually in the grid that the data told us you went to school or college in. So we removed that kind of data as well as part of our cleaning process. Sorry, the map there is just the greater Dublin area. So you can see it includes Dublin County as well as the surrounding counties. So we're capturing anybody living, working or studying in those counties. So we now have the population's home location and the work location. When I say population, this is our agents that we're going to use in our simulation. The next thing we needed was the road network. So we needed to tell the simulation what the road network looked like, and optionally what the transport or the public transit network looked like if we were going to start simulating public transport. So essentially all MathSim does is route agents from their home to their work location via the road network. And as I said, it does this recursive iterations to try to reduce travel time and avoid congestion on each iteration of the simulation until an equilibrium is reached. So just to recap where we got this, the initial demand from was this POWSCAR, which is part of the census, place of work, school, college, anonymized records. That gave us the home location, the work location, the departure time in the morning, and the school and college location. So it gave us a good, the first kind of building block of the data that we need for our simulation. The road network we got from OpenStreetMap, which is an open source map of the world contributed by volunteers. It's a volunteers geographic information project, and it contains links and nodes representing the roads and the intersections, but it also contains information such as speed limits, number of lanes, and the class of the road, which is obviously important because these rules will be part of what our agents follow. So they know the speed limit on the motorways, for example, is different from primary roads, and they will adapt their speed to and their travel time to account for that. So it's important that we have this accurate information to create a really, really realistic simulation. Okay, so here's some of the input sources. This is a map really focusing on Dublin. We can see all of those dots on the map represent locations of homes. This is the road network that we used, extracted from OSM. So all it is from OpenStreetMap, all it is links and nodes, and obviously then all the additional information such as the class of the road and the speed limit is encoded there as well for our simulation. So I said that we want a really detailed and really realistic, I guess, simulation of Dublin. And so far, all we have is a small area to a 250-meter grid. But traffic, of course, is going to be occurring in that small area, and it's in that 250-meter grid. And if we didn't have more information at a finer grain, a finer spatial granularity than that, our simulation wouldn't be great. So what we did was begin some data fusion. So the geodirectory contains a database of all buildings in Ireland, and has some additional information about the buildings, such as the type of building, if it's commercial or residential, and maybe also the activities that are going on there. So is it an educational commercial building? Is it a manufacturing? Is it office, and so on? That's all encoded there. So what we wanted to do was, rather than saying this person lives in this 250-meter grid, we wanted to assign them to a building, which is a residential building, in that 250-meter grid, so that we would start to see traffic flow within our small areas as well. So we did that, and these two maps here show some differences. So the first one is when we applied, or when we assigned our agents to individual properties. So they're all houses that people are in, or homes that people are in, apartments and houses. And the lower map then is the commercial property. So this is where people work. So you can see a difference there. It's showing the same area. The first one showing where all the houses are, or where all the homes are, and the second one is showing where all the commercial places that people work are. So we've now gone from a situation where we just had really people anonymized to working in a 250-meter grid, or to living in a small area, to an actual property. Now, it's not the actual property that the person lives in, but it's a reflection of potentially how the population are distributed in that small area, and how the population work in the 250-meter grid. So just more detailed, finer spatial granularity. Okay, so at that stage, all we have is where people live and where they work. There's a lot of stuff we still need to get or to find out before we can really do an accurate simulation. So the majority of trips are home, work, home. So people just start in their home in the morning, go to work and return home in the evening, and they use their car for that. But there are also other trips which are more complex and more complicated that people do. They might go from home to the gym to work and then home. They might do shopping on the way home. They might visit friends. They might go to the cinema. There's a whole host of different things that people do during the day using their cars. And to create an accurate simulation, we want to know about that. That information is not captured in the census. You didn't fill in information about that. But there is a national travel survey, and we looked at the details of that. So it's a small survey in that the 16,000 people kept a travel diary, and basically they just said where they went during the course of their day, and they kept the travel diary for a couple of weeks, I think, and they just specified their activity chains, is what they're called, so the activities they did during the day, and they included the mode of transport, and they included the times that they did these things at. So we were able to find out about people's habits in terms of school, shopping, sport, doctor, visiting family and friends, and the entertainment which they did during a day. But the travel diary, while really useful, it was more or less exactly what we have here at the bottom. So somebody started at home, they went to school, they went to work, then they went shopping, then they met friends, and then they went home. And there may be times associated with those, but what's missing is the location. And that's key for our simulation. You need to know where they went to do their shopping, where they went to meet friends. And we didn't have that from this travel survey. So we needed to figure that out, or to determine how to translate these activity chains into the locations that people are going to do these activities at. So where? So if shopping is the next thing in your activity chain or in your diary, there's multiple locations that you could have done your shopping at, and we don't know where that occurred for sure. So we started to look at the research and look at the literature around this about location choice. And we developed a model to model where people are likely to go to get their services, to get their shopping. So initially we had to look at where all the facilities are located. So where are all the shopping centers, where are all the individual shops, where's all the entertainment venues, where are the sporting venues, and so on. So we had to get those. We got them from OpenStreetMap as well, which I mentioned previously. So we had the locations. Then we wanted to know what kind of capacity they had. So what's the interest in them likely to be? Because we wanted to produce an attractiveness score. How likely is it somebody's going to be attracted to one of those shops? So in the absence of other data, we simply looked at the size of the facility. And one thing that we can use to gauge the size of the facility is the number of parking spaces. So on this map here, you can see the larger circles around the periphery of Dublin. They're all shopping centres. So shopping centres have a big attraction. They've got a lot of car parking spaces, so they're not going to build those car parking spaces for no reason. They're building them because they expect them to be used by people, so they expect them to have a certain attractiveness score. Smaller shopping centres have smaller circles represented in them, and then individual shops only have a couple of parking spaces, but we've still mapped them. So that's kind of what we're using as an indicator of how attractive a location is, and building a probability that somebody's going to visit that location to fulfill their shopping needs. And we base this on the radiation model for individual spatial choice. So when you need to go shopping, you have a choice of where to go. And we use this radiation model, and it's based on demand. So your demand can be filled in multiple locations, but locations have a certain attractiveness, which we use as the capacity of the location. Now, radiation models and spatial choice models are typically used for determining location, or determining the number of people that are going to travel from one area or one region to another region. So from one city to another city, for example. We've had to adapt that to a much finer grain of going from one building to another building. So it's kind of really one of the first uses of this, where it's going at such a small level. That's all based on the capacity scores. We could use other capacity scores or attractiveness, but we saw car parks as being a good option for this. So now we know where you live, where you work, and we have modeled where you're likely to go to fulfill your shopping and entertainment needs based on this radiation model for location choice. The next thing that we saw in the activity diaries was people went to visit friends. So again, we need to see where these friends were and where you're going, how you're going to use the road network to get there. So again, we didn't have any raw data about this, but we had other studies. And the other studies that we saw show that geography is really important in your social network for friends that you're going to visit. And that the probability of friendship actually decays with distance. And communities tend to be spatially related. So your friends tend to either be associated with where you work or where you live in the main. And the data that are the studies that we looked at for this had used call detail records. So they'd used mobile phone records to see the interaction between people. So where someone was calling from and where they were calling to. And this showed how individuals were connected. And the map produced in this study for Dublin, actually, these are the data for, show that there's these kind of communities within Dublin. So people in the green zone tend to call people within the green zone. People in the red zone tend to call people within the red zone. And that's the kind of community structure that was identified. And in the absence of another approach to see where our friends were, we use this community structure. So if in your activity chain, it says that you're going to visit a friend and you live in the green zone, we picked another individual randomly within the green zone. Now, the number of friend visits compared to the number of commutes and the number of shopping trips was quite minimal, but we still wanted to model it. And this was one approach that we saw for gathering the data to model it. Okay, so I'm near the end now because we have nearly got all of the data that we need for our simulation. So we have the locations of facilities for shopping and entertainment. We have the home locations where you live. We have your work locations. We have your activity chains. That's the thing you're going to do during the day, which we've used to produce a schedule for each agent. We have your social network and we have your location choice model. So the important thing is for each agent in our simulation, we produce a daily activity chain, which says where they will need to go or want to go and the time they want to do it. And that all gets fed into MatSim, into our simulation, along with the road network. And MatSim then does its magic of producing these simulations, trying to ensure that everyone gets their locations, does their whole day's activities while minimizing the travel time. So it produces outputs. The output that it produces is the hourly traffic volumes on different roads. So that gives us a good metric to compare because we have the real traffic volumes on different roads in Dublin. So you can compare the output of the simulation versus real life ground truth. So we validated against traffic on the M50 and the M4. So there are two motorways in Dublin. One is kind of an orbital motorway, the M50, and the M4 is heading out of Dublin. So we compared what the simulation was telling us in terms of the number of vehicles using those bits of the road for each hour versus the actual ground truth that we had from the National Roads Authority. We were interested in our radiation model because, as I said, that was a new thing where we were using the radiation model at a very fine-grained level. So we wanted to see was that performing well. And we compared that to a nearest neighbor approach. So MatSim's inbuilt location choice model is a nearest neighbor approach. What that means is if you're in work and your next activity is shopping, it just routes you to the nearest shop, which doesn't seem realistic for the reason that I outlined. Certain shopping venues are more attractive and you're more likely to go there. There's a probability of going to different ones rather than just going to the nearest neighbor. So we'll see what the results were for that. This is just some of the outputs. It produces some nice animations. If people are interested in the MatSim outputs, it produces these this animation, and all the green dots there represent vehicles moving. The red dots represent vehicles that are stuck in traffic. So we can see 6 a.m. people are starting to come in from the west of Dublin along the kind of the main commuter routes, and then by 8 a.m. there's already a lot of traffic on the motorways and on the routes all approaching the city centre. And then 8 p.m. is the final image there, and again things have calmed down. There isn't as much congestion. So the red is congestion. Different levels of red mean different levels of congestion, or it's really the speed the vehicles are traveling at, and green is more or less free flowing. So as I said, we compared the road count at these 3 locations, numbers 1, 2, and 3 on our map here. And this is the results that we got. So firstly, the raw data, or the ground truth, is the dashed black line. That's the observed. That's what actually happened. That's the counters embedded in the road network counted this number of vehicles. Our simulations are the 2 other colors. So we can see this is on the M50 heading northbound. The morning peak starts kind of rapidly just after 6 and finishes around 9:30, 10 in the ground truth. And our simulations capture the same peak in the morning and again the peak in the evening for the kind of the 2 main commuting times. The main interesting thing is that the orange line, which is MathSim's nearest neighbor, it captured the morning commute and the evening commute quite well because that data was given to it, but all the discretionary trips were missed by the MathSim nearest neighbor. So everybody was going to their nearest shop. So they weren't using the M50, for example, in this case. But our approach, which is the green line, did capture this kind of discretionary trips in the middle of the day, which aren't necessarily commuting trips. It captured them quite well and improved certainly on the nearest neighbor approach. And we also used Ballinteer Southbound. So again, morning and evening, there is differences. This one, you know, the peak is not as high for either of the simulations as it is for the observed. We have some ideas around that. And similarly, it's lower throughout the day. But again, what we're interested in is this difference of the green line where we use the radiation model for location choice and the improvements that we got in getting nearer to the observed. And then this is another motorway leading out of Dublin. It's heading westbound. So the big peak is in the evening as people are leaving the city to head out of the city, out of the city or out of Dublin, and that's what's captured here. And again, we weren't so good with the discretionary trips here where it wasn't within Dublin, but we were better than the nearest neighbor approach. Some of the reasons for the discrepancies are, if you think back to the data that we're using, we're only interested in private vehicles. So we don't have any commercial trucks or delivery vans and other service vehicles that are on the road network aren't included in our simulation. So we're obviously going to be a bit off in terms of that traffic is still obviously being captured by the ground truth. So just to wrap up, sorry if I've gone a little bit over, but it's we've created this realistic large scale traffic simulation for Dublin, which shows not just the commuter trips, but also the social and leisure related trips, which are discretionary trips. Our simulation used 500,000 vehicles, or 500,000 people, which is a 50% sample, and we were able to scale up the results then easily. We got the commuting patterns from the census. The social network was from the mobile phone logs in another study, and the leisure and shopping trips were developed using the radiation model. There's a lot of stuff that you can actually do with this approach or with this simulation. So it does work for public transport, and the census data has the public transport, so we could simulate that as well. The moment we focused on midweek, so we focused on working days. We could also look at the weekends and the impact of large events. So for example, we would know how many people are going to a certain stadium, if they're using public transport, if they're using private vehicles, and what impact that's going to have on the traffic network. The role of habit can be kind of important. So at the moment, there's a probability that somebody goes to a certain location. But also there are studies which show that if you go to a location more than once, you're probably going to go to it again and again. So you're likely to go to the same shopping center. At the moment, our radiation model doesn't account for that kind of habit. Each time the iteration is run, it's a fresh look as if you'd never visited any shop before, what's the probability of you going to all of these other shops. But I think habit could be important there. As I said, studies have shown that. We could incorporate that. Other things are the use of electric vehicles. So charging stations, optimal locations for charging stations could be included in this study, and the variable road pricing. So if we want different prices for roads, if you're an electric vehicle, or different prices if you're not an electric vehicle, or indeed certain roads only being allowed for electric vehicles versus non-electric vehicles. That can all be studied within the simulation. But the important thing is that you have an accurate baseline. You have the current scenario, the current Dublin scenario, and then you can start changing things to see how it impacts, how these changes will impact. And that's the important thing. And that's what we've created with this study. Through all of that data analysis and data preparation, really, to be able to create a realistic simulation. So thanks very much for listening. I hope you found it interesting. And I'm open for any questions you might have.